To listen to the forest, you have to go silent. Here is a blimp quadrotor quietly monitoring bioacoustics in the wild. There are many different types of drones that can be considered for such tasks. These include multi-rotors like quadrotors, fixed wings, and blimps. Out of these, miniaturized omnidirectional blimps like Janus triumph over other designs by providing high agility and a high battery life. But even platforms like Janus and other blimp designs found in literature all possess a single helium reservoir which takes the form of a latex, PVC, or mylar balloon, and it is responsible for generating lift. These platforms are at a risk of failure from accidental balloon bursting. None of these blimp platforms have any mechanism to sense or recover from a balloon failure, which ultimately proves to be catastrophic for the system. Certain application scenarios like outdoor animal monitoring benefit from the effortless hovering made possible by blimps. However, these may also bring out encounters with malicious agents like poachers who are inclined to shoot these blimps down. This necessitates a method for recovery. This can be done by augmenting omnidirectional blimps with balloon failure sensing and quadrotor morphing ability, as it is much harder to shoot down a quadrotor than a blimp. Presenting Janus, a morphing quadrotor blimp with balloon failure resilience for mobile ecological sensing. Our quadrotor blimp hybrid takes inspiration from blimps by leveraging their inherent battery life advantage while also possessing balloon failure resilience. Our platform can morph from a blimp to a quadrotor upon sensing failure and still carry out the mission. This ability is possible due to our failure sensing and transition mechanisms, which leads our platform to be able to behave both like a blimp and a quadrotor as and when required. In the blimp mode, we use a 4-propeller design where each propeller is placed horizontally to allow omniplanar motion. In this configuration, we only need to power a single or a pair to move in a plane. We can also use the propellers to translate vertically or yaw in place. In this configuration, we can use the helium to float while collecting data. This does not require any power as we can hover with neutral buoyancy without powering any motors, moving only when really needed. We can carry different payloads based on which the balloon size can be scaled. Here, Janus is seen carrying an RGB camera, which is an example payload and can be used for capturing its surroundings as well as tracking a human in sight. Our sensor suite comprises of 3 different sensors, a single pole TE connectivity piezoelectric film, an APD S9960 proximity sensor, and an BMI 270 accelerometer. We test the failure sensing subsystem using 2 different balloons made of latex and PVC. The balloons are 60 cm in diameter. We additionally also test the system with 23, 45 and 90 cm balloons. We evaluated different scenarios like collision with trees, branches, and other small objects which the blimp might encounter outdoors. These could potentially be registered as false positives by the accelerometer or piezo when detecting balloon failure. Different false positives were also evaluated for the proximity sensor, which uses infrared light for balloon detection. These included mirrors, balloon material, and balloon distance. The response from each sensor was evaluated to distinguish actual balloon failure from false positives. Each sensor's output was passed through a sigmoid function, multiplied by a weight, and finally summed to give a final fused value. This value was then compared against a threshold which led to a failure decision. Multiple tests were conducted to test the balloon failure sensing algorithm. This was conducted with different balloons as well as with different states of the propellers, moving as well as stationary. The tests were used to characterize the performance of the algorithm as well as record the response time. This was done using LEDs and a high-speed camera. Using our sensor algorithm, we could detect balloon failure in all of the cases. The average detection time was found to be 38 milliseconds with a worst case detection time of 66 milliseconds. The morphing design is enabled by constrained 90-degree rotary joints between the motor arms and the platform body that allows them to be vertical in blimp mode or horizontal in quadrotor mode. The system transitioned from a blimp mode to quadrotor by using the linear servo to disengage the clutch. This releases the tension in the reel, allowing the rubber strips to pull the motor arm upwards. The system allows for recovery from an erroneous failure detection. This can be done by transitioning back into blimp mode from quadrotor mode while the balloon is still intact. The linear servo engages the clutch where the DC wind-up motor pulls the reel. This pulls on the motor arm, adding tension to the fishing line, ultimately pulling the motor arm down back into blimp mode. Janus is designed for low altitude sensing, complementing other drones for wildlife monitoring and data collection.